Okay, this is an AC transformer. It's been removed from a microwave oven. This transformer generates high voltage in the oven, and it takes 240 volts normal input on this side here up to about 2,400 volts on the output side, which is used for generating the microwaves in the oven. In order to get this transformer to work, we have to supply AC to it. I am currently supplying 8 volts in. If I put a voltmeter across here, it will read 8 volts, and I'll show that to you now. You can see that's on 0 AC. I'm going to bring it across here, wire it up. The input there is 8.1 volts AC. Okay, now we have to get an output reading from this transformer, and we're going to get this output reading by going directly onto the case, onto the output wires of the transformer. Not the case, I've removed that. Now if we put this into here, we're going to get, hopefully we've got a stable output of about 80 volts. No, not getting anything yet. There we go, 82.8 volts. So the amplification factor is about 1 volt in to 10 out. Can you please change the input to 10 volts in, please? Okay, we've now got 105 volts coming out, and we'll go up to 12 volts. Okay, the maximum that we're getting out of this is now about 127 volts. So it's going in at about, every volt that's going in is being multiplied up by a factor of 10. Okay, so I'll turn off the power now, and I'll pull this apart and have a bit of an explanation. Okay. So what you can see if you look carefully at this transformer is you've got 2 sets of coils. You've got these coils here, which is the input coils. The wire is actually quite thick, whereas in here, if we can have a look at that, the wire is much thinner. The reason for that is that the input coils carry a lot of current, and so they need to be thicker to carry that current without any problems. The output coils, on the other hand, are carrying high voltage and low current. And so because the current's lower, they don't have to be very thick, and furthermore, we want about 10 times as many of these as we do the input, so it's much better to use thin cables on your output if you're using a step-up transformer. Now this is working as a step-up transformer because in the normal course of events we take 240 volts in here and put 2,400 out here. So it's stepping up in voltage. If on the other hand we were to make this the supply side, we would step down. So if we put 240 into here, which I'm not going to do, we would get 24 out over on this side. So I've discussed the windings, the ratio of the number of coils and their various thicknesses. The next thing I'm going to talk about is heat loss. And basically what happens in the normal course of events is we put electricity into here. The electrical power that we feed in on this side goes out in 2 places. It goes as output power out here, and it goes as what's lost in the transformer. Now, when it's lost in the transformer, it's basically given off as heat. And there's various things which have been done in order to minimise heat losses in this transformer, and which are also done in other transformers to varying extents. What you can see from this transformer here is that if you look at it this way, the change in magnetic flux as a result of what's going on in these coils is going to be changing a magnetic vector like that from north to south. The magnetic field will be changing in that plane. As that happens, inside the iron core, it would normally generate an electrical eddy current. And that electrical eddy current would normally make this core very, very hot. So what they've done is right through the core, they've made it out of laminated steel. You can see it right around there and right underneath and right through. And each one of these plates is insulated from the next. So the only way you can get an eddy current to run in this thing is to get it to run up one very narrow plate, crosses the plate, and then it has to go all the way back down the plate and back the other side. So these eddy currents are dramatically reduced as a result of lamination in the correct plane. On the other hand, if the lamination was this way, then the eddy currents would run quite happily and it wouldn't work. So the aim is to minimise the wastage of heat from eddy currents, and that's done by lamination. There is another method of doing that, and it's described in the textbook here. Oh, it's not another method of lamination, but it's another method related to minimising heat loss. And what it says is, another method for reducing eddy currents losses in transformers is to use materials called ferrites, which are complex oxides of iron and other metals. They are good transmitters of magnetic flux, but poor conductors of electricity, so the magnitudes of eddy currents are significantly reduced. So in order to answer questions about how is energy loss reduced in transformers, there's two main things, the first of which is lamination, and the second of which is to put ferrites into the cores. There is another method of keeping transformers operating at a good operating temperature, and that is sometimes they will cool the core of the transformers with oil or water running through various different alleyways. So that's all three methods at least mentioned. The only other thing that there really is left to say about these transformers is that on this particular setup here, I put in, say we put in 10 volts, and we'll move that back to 10 volts. We're putting in AC at 10 volts, and we're getting out what will be 100 volts DC, as I will show you. There it is again, there's our 100 volts DC. You can get this transformer to generate a transient voltage using a battery. And the reason for that is if instead of connecting this to AC, you connect it to the terminals of a battery, at the point at which you switch it on, there will be a build-up of magnetic flux in here, which will then lead to a transient voltage being generated on this voltmeter. Once the current has stabilised from the battery, then that voltage will fall to zero because the magnetic flux won't be changing. And then when you disconnect the battery, the current will fall away, the magnetic flux will fall away, and you will get a transient voltage on the voltmeter. But in the normal course of events, for reasons that have been explained, you need AC to get the transformer to work. Okay, so that's pretty well it.